Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Tortuga Logic with Jason Oberg, and we're going to talk today about CWE. So, Jason, what is CWE and why is it so important?
CW stands for the Common Weakness Enumeration. It's a database and a taxonomy for actually classifying weaknesses for both hardware and software. In early February of 2020, there was actually a release of hardware-specific CWEs, and this has been a great initiative because it helps classify and reason about specific types of weaknesses in hardware.
How new is this? When did it first come into existence?
So I believe CW itself has been around since about 2006, and the hardware weaknesses, the hardware-based CWs, were just introduced recently in 2020.
Let's take a closer look.
Sounds good.
Jason, what are we looking at here?
So we're really looking at two different use models for hardware CWs in organizations. Use model number one is really applying hardware CWs as an invaluable security metric. What we really see being done there is that, for example, organizations will look at their internal designs, they'll try to classify what weaknesses are relevant for the designs, and they'll actually list all of those weaknesses out based on the CW database and try to figure out which ones they're compliant to and which ones they're not. So for example, maybe CW 1189 that they have some mitigations for and they have a security verification plan for, they can then validate that they're compliant against covering CW 1189. Same may go for CW 1191. And then there may be other CWs that throughout their verification process or their design process, they see that they're actually not compliant and they can actually see, I'm not covering CW 1231 for whatever reason. Maybe the mitigations aren't properly implemented, or maybe they've made some design decisions that expose them to that weakness.
And this becomes even more critical as we get into heterogeneous designs too, right? Because now maybe you're buying a chiplet. Does that chiplet have a weakness that you need to understand?
Totally. You know, as we see more and more complexity getting into designs, both from being more heterogeneous as well as becoming more just hyperscaler, we see a lot more of these types of weaknesses being introduced. I mean, really, security hides in complexity. So as we see more and more designs becoming more complex, we see a lot more of these weaknesses becoming more prevalent.
Who determines whether those weaknesses are actually there, though? So a vendor that's selling a chiplet, for example, do they now go through and say this has a weakness, or does somebody else identify it?
That's a good question. So most of the weakness classification is actually done internally. So companies, organizations will go through and try to identify whether they actually are exposed to any of these types of weaknesses. Where they come up again is actually in another use model if an actual vulnerability is identified in the field. And at that point, they'll actually take the vulnerability and classify which weaknesses were used to actually exploit that vulnerability.
So explain how a weakness compares to a vulnerability.
Yeah, it's a good question. I think it's often a confusing topic. In its simplest form, a vulnerability is an actually identified issue on a real product. So oftentimes you'll get a CVE number attached to a specific vulnerability, whereas a weakness is what an attacker actually used to succeed in exploiting that vulnerability. Yeah. For example, in Meltdown, the CVE is CVE 20175754, whereas the actual CWE that's associated with this is CWE 1264, which 1264 is actually related to desynchronization between data and control, so it's essentially a race condition. But the actual CVE is actually tied to specific products that were vulnerable to this actual vulnerability. So you can be exposed to this weakness, 1264, and no one's actually ever exploited it yet, but you still may be vulnerable.
If you don't have any known weaknesses or vulnerabilities, does that necessarily mean that what you're selling there or what you're buying is more secure?
So I think if you take a weakness-based approach and you have metrics, as I talked about here, you can have a lot more quantified and measurable assurance on your actual security. It doesn't mean you're not vulnerable because, for example, if you determine by your threat model that CW 1231, for example, is not in scope, an attacker may go and exploit that weakness in your designs and you end up with a vulnerability. But that said, if you go through a systematic approach of figuring out which CWs are relevant for your design and systematically design and verify your chips to address those common weaknesses, then you can have a measurable assurance that you've actually met that. So if you're not susceptible to CW 1264, you're not going to be vulnerable to Meltdown, obviously, but also any type of variant to Meltdown as well.
Well, you think about Meltdown. Meltdown really capitalized on something that was being done for years in order to speed up processors. It was an accepted way of doing it. Suddenly it becomes a vulnerability, 15, 20 years after it's already been introduced, right?
Mm-hmm. So this is a common game, right? So security is always an evolving target. And that's the same reason why we see new CWEs being introduced. It's not a fixed thing in time. It's being evolved. I think right now the hardware CWE database has over 100 weaknesses. I think when it started, it had maybe about 20 or so. As attackers get more sophisticated, we're going to see more weaknesses added, and obviously we're going to see more vulnerabilities being identified as well.
One of the drivers here is that the value of the data is rising. So you think about an automobile, for example, that data that's moving there can actually determine how the car behaves. You need to understand all this stuff up front, but can you really do that? Can you push a button and say, hey, we know what's going to happen here if you use this part?
So I think it's a very good observation because security is basically tied to what an attacker will actually gain, right? It's a return on investment for that attacker's time in trying to break into your system, right? And so as the value of what they receive goes up and the cost of them doing it goes down, you start seeing more vulnerabilities. And that's really the shift that we saw on the hardware side, because the actual ability to actually exploit hardware-based vulnerabilities became more plausible remotely. We saw that with things like Meltdown. We see it with Rowhammer, these types of attacks. And as that continues to grow, we're going to see a lot more attackers actually leveraging that because it's easier than other mechanisms of actually breaking into the system. And so, you're exactly right that as the value of what they aim to gain by breaking into hardware grows, as well as the cost of that is decreasing, they're going to continue to do that.
So in theory, every piece of hardware can be cracked, right, by a nation state would throw enough resources at it. Do those show up as weaknesses and vulnerabilities?
A lot of the original hardware attacks were rooted in kind of radiation tolerance, fault tolerance, and anti-tamper, which is very much driven by a lot of government applications for space and so on. And so there's a lot of semiconductor companies that sell into that market have products that are very well geared towards those type of attacks. And so they're actually pretty resilient against those types of attacks. There's still ways of getting around these things, as there always is if you have enough time and enough money. But the downside of that is those types of techniques and products are extremely expensive, right? So they just, from an economic standpoint, it doesn't make sense to sell those into markets that don't have nation state attackers as part of the threat model.
What happens when a chip is already out in the field, has been potentially updated multiple times as well?
Yeah, this is a tricky thing, and actually it's a big concern for, if you think about some devices, they have, some semiconductor devices have, 15 plus year lifetimes. So how do you plan for the future from a security perspective if you don't know what attackers are going to do? And honestly, it's I don't have the golden answer, but there is some balance of updatability. So you need to, in a perfect world, you could be fully adaptive. You could actually update your whole system if you found an issue. But at the same time, there's security implications with doing that. So a lot of times, the designs are erred on the side of don't update at all because that's more secure. But then if there's a vulnerability found, you can't fix it. So I think it's important that when we design systems, we think about, as part of the security program, I think it's important to think about and assume that vulnerabilities are going to come up, and you have to have a way of reacting to that. Whether that's a plan to actually replace the chips or a plan to actually issue firmware updates, but basically an incident response plan as part of your organization so that you can actually manage those types of things because they will come up.
And this is a real-time update that you need too, right?
You need. I mean, you could obviously RMA the chip and get it back and actually do the update. Remote updates have their own issues on top of that as well, but that's obviously the most economical. So.
Is there any chip out there that is not vulnerable to anything?
From my perspective, no. Every single one, depending on its use model, has a specific exploit. Basically, from an attacker's perspective, if they can cause changes in behavior in the system, extract information, or just cause it to no longer work, and that gives them some gain, then pretty much every chip is vulnerable to those types of things. Even if it's a pure analog chip doing something that's, like an A to D converter or something like that, you can actually mess with those types of devices potentially and cause changes in behavior in the system. Obviously it doesn't get as those aren't meltdown type of vulnerabilities, but the, tampering with the chips themselves, whether it's physical or remotely, which, would be a digital based SoC, can still have negative effects on the system, and attackers may be motivated to do that if that gives them some benefit.
But this may drive companies to say, oh, we found a weakness in our hardware. We need to tear out all the hardware, and what they put back in may not be any more secure, right?
Yeah, honestly, from my perspective, if that first level is reached, so just thinking about the problem, I have this chip, it's going in this system, what can an attacker do to this chip? And that's written down with, using CWEs as a metric for helping reason about that. You're already going to be leagues ahead, because you're not going to think about everything, but just having the discussion and having as part of your plan is already going to make you a lot more, your security assurance for your organization as well as your products is going to go up dramatically.
Jason Oberg, thanks for a great explanation.
Thanks, Ed.